All right, hello everyone. Welcome to the first part of the video for section 3.2. So moving on to studying a specific type of polynomial now. The specific type of polynomial we're going to be looking at are quadratics. Okay, so first of all, what we're asked to do here is use our knowledge of transformations to write an equation for the quadratic function represented by the graph below. So first of all, hopefully you keep hearing that term quadratic, you think of our toolkit function, right? The one that looks something like this. That has the equation f of x equals x squared. And hopefully you would agree that the graph here in the picture is a transformation of that one. And in fact, here in my picture, I'm going to add that graph so that we can use it as a reference while we are figuring out the transformations here. And that is absolutely awful. Let me try again. Okay, something more like that. All right, so let's first of all figure out what the transformations are. And the first one that I see, the big one that I see, is that the original function f of x equals x squared is the tails are going up, it's facing up. And this new one, we see they're facing down. So because of that, we know there has been a vertical reflection. Okay, and in fact, I'm going to draw that, what that would look like. So this has happened. And then if we focus in on the vertex, so this point right here, I can see that that has been shifted 1 unit right. Okay, and then it's also been shifted up by 2 units. All right. And then there's one more transformation here, and try to draw this as best I can. So going from the orange graph, we said that the to get to the black one, we shifted 1 to the right and up 2. And if we did that, then our graph would look something like this. Okay, but notice that is not the shape we see, right? Okay, the one that is there is a little bit wider, almost like it's been pushed down from the top and the bottom, and oh, that probably means there's some sort of a compression going on here. And how do we figure out the factor of that compression? Well, the method I'm about to show is not an exact method, but I think it works. So notice that in the red graph here, right, if we go over 1 unit, we go down 1. If we go to left 1, we also go down 1. But in the black graph, right, notice this if we start the vertex here, whoops, darn it. Start the vertex here and go to the left 1, we actually go down about 1/2. If we go to the right 1, we also go down about 1/2. So that tells us that because that up or down thing there has been changed, that we have a compression by 1/2, and it also looks like it's vertically, right? Because it impacted how much we had to go up or down, but not left or right. Okay, so let's use this information now to write the equation for this black graph. And we're going to start with the toolkit function, the f of x equals x squared is our base. We have to think about what each of these things here means. And I'm going to do this in green. Call this function g of x. So the vertical reflection, first, that means there should be a negative sign out front, right? The shift 1 to the right means on the inside, that's where we put that. And because it's on the inside, it's a house of lies. So rather than being a +1, even though it's going to the right, we're going to have a -1 squared. Shift up 2, well, that's an outside thing, so it means we put a +2 on the end. And then the compression by 1/2, since we decided it's vertically, that means a 1/2 goes here out front. So if I try to write this out a little more legibly, what we get is g of x equals negative 1/2 times x minus 1 squared plus 2. Okay, and you can check with your graphing calculators that this equation, in fact, would give us this picture or this graph that we have here. Okay. All right. So as I mentioned, we're studying quadratic functions in this section. And there's a couple of different forms we'll see quadratics written in. And then some, and then there's going to be another piece of vocabulary here we need. So first of all, if you're talking about a quadratic function being written in standard form, it's this one, this f of x equals ax squared plus bx plus c form. Okay, so an example of something like that might be f of x equals 3x squared minus x plus 1. Okay, that's an example of something in that standard form. Now, as per normal, I will caution you is that for something to be a quadratic or to take this form, it does not necessarily have to have an x as its variable, right? We could have something like v of t equals t squared minus 4t plus 7. This is still a quadratic, and it's still in standard form because it has that ax squared plus bx plus c form. Okay, the next one is transformation form, which is actually what we were just looking at. So one that we can read the transformations off very quickly to figure out what is going on with the function. So the general form there is f of x equals a times x minus h squared plus k. And if we connect that to the one we just did, the gx equals negative 1/2 times x minus 1 squared plus 2. Notice right below that I can write this f of x equals a times x minus h squared plus k form. Okay, and we can see the a corresponds to negative 1/2. The h, notice that it corresponds to the plus 1 here, not a minus 1, because the h already has a minus in front of it. And the k corresponds to the plus 2. Okay, with the k value, k with the k, see what I did there? Okay, anyways, the k value keeps the sign with it there. Now, also notice that if we look at the values h and k from the formula I just wrote down. Okay, well from ours we see that h should be 1 and k should be 2. Again, h is not negative 1 because in the formula it's a minus h and we have a minus 1, so it means h is positive 1. And if we look at those points together, notice that they describe a special point up here on the graph of this quadratic. And so they are that representing that peak there, that point. And so that tells us that those values h and k give us the coordinates of the what's called the vertex of the quadratic. Okay, so it says here the vertex of the quadratic is located at h comma k, where h and k are the numbers in the transformation form of the function. Because the vertex appears in the transformation form, sometimes the vertex or the transformation form is called the vertex form. The moral story there is this form here can help us identify the vertex of a quadratic. Now, a couple other pieces of vocabulary, just a couple things to think about. Number one, we call the shape of a quadratic here. You may have heard this before. It's called a parabola. Okay, and that's spelled P-A-R-A-B-O-L-A, parabola. And the other thing I want you to know is that regardless of whether the quadratic function of the parabola opens up or down, that quadratic function will always have a vertex. So for example, this one I just drew there in blue still has a vertex down here at this lower point. Okay, so it does not have to be flipped upside down. All right, and it turns out we can find the vertex of a quadratic even if it's not, if the given equation that we have is not in transformation or vertex form. So if we have it in that standard form, so again that was that f of x equals ax squared plus bx plus c. This slide here gives us a formula for finding the values of h and k. So first of all, for the value of h, we do negative of b divided by 2a. And then once we have that, to find k, we just take the value for h and plug it into our function. So we take whatever negative b over 2a is and plug it into our function f to find the value for k. And then we would have the coordinates of our vertex. So let me show you an example of that. So here at the top, we're asked to find the vertex of the quadratic function g of x equals 2x squared minus 12x plus 1. Again, note that this is in that ax squared plus bx plus c form. So to find the coordinates of the vertex, we first start by finding h. We do that by doing negative b over 2a. So using the numbers that are here in our equation, we have the negative of negative 12, all divided by 2 times the value for a, which is 2. And notice those are just the coefficients I plugged in there. I didn't plug in any x's. Okay, a and b are coefficients. We have the negative 12 on the top, which gives us a positive 12. 2 times 2 on the bottom, which gives us 4. So I'm doing 12 over 4, which is 3, is our value for h. And then recall that to find k, once we have h, well, we just plug the value for h in. So we do g of 3, which is going to give us 2 times 3 squared, minus 12 times 3 plus 1. Work that out. Let's see, 9 times 2, 18. 12 times 13 is negative 36 plus 1. So that would be 18 minus 36 is negative 18 plus 1, negative 17, I believe, would be our value for k. That's what we get from plugging 3 in. Yep, I believe so. So then we know that the coordinates of our vertex for this first one, again using the HK method, are going to be 3, comma, negative 17. Okay. All right, and then the last thing we're asked to do, find the vertex of the quadratic function given by the formula f of x equals 2 times x minus 3 squared plus 1. Notice now we've got that transformation form, the a times x minus h squared plus k. So to find the coordinates of the vertex, well, we can just read h and k straight out of that equation. So h again will be 3, and notice again it's not negative 3, it's just 3. And the value for k, plus 1 there, so it looks like that would just be 1. So the coordinates of the vertex here would be 3, 1. All right, great, that's all for now. Thank you for watching.